We can usually characterize inferences as psychological processes that transform information. But let's talk a little bit about some of the important functions that inferences subserve in cognition. Well, for starters, inferences generate new explicit and available information, and they can also adapt existing information to novel circumstances. Inferences allow us to evaluate and integrate new information into our belief systems and our worldview. They help people to adapt to the world by transforming information into useful formats, making inexplicit information explicit, like we did with the Olivia travel problem. Inferences even allow one to discover inaccurate information, poorly evinced information, and inconsistent information, so that one can discard that bad information and or render one's worldview more consistent. Given the many important functions that inference seems to subserve in cognition, what are the properties that we might want to optimize in inference strategies? Well, one property might be power. The ability to take a small amount of information and to extrapolate from that information to other information far in the future, far in the past, to see underlying structural details of problems, things of this nature. Of course, one of the primary benefits of good inferences is truth, or probability of truth. Truth is important because in order for us to have adaptive interactions with our environment that help us to survive and to thrive, we actually have to be able to represent the environment as it is. So powerful inference strategies that aren't reliable, that don't generate truth or accurate representations of the world, they aren't particularly good. Finally, of course, we'd want speed. Making inferences fast, being able to adapt on the fly. That is also important. You want to be able to identify that tiger as it runs towards you long before you're actually in danger. Now, in a complex and highly variable world, these three features are very rarely even close to being optimized. In fact, probably the visual system is the closest things human beings have to a powerful, fast inference system that tends to produce true beliefs. But of course, there's a whole chronicle of visual illusions to illustrate the fact that it, too, isn't perfect. So what happens in a complex and variable world is that trade-offs are made because, as Larry the Cable Guy says, you gotta get her done. In other words, tractability is probably the single most important feature of most of our inference strategies. Tractability is the ability to use the resources that you have available to you to generate a solution within a time frame such that the solution actually makes a difference. So oftentimes what you'll find is that inference strategies will represent a trade-off between truth and power, or truth and speed, or power and speed, in order to make sure that you get tractability. No inference strategy is valuable if it doesn't give you an answer that you can use in a time frame in which you need that answer. So when we think about inference strategies, we'll have to recognize that in general, they're trading off truth for power, truth for speed, so on, all with the goal of trying to get a tractable strategy, one that answers the question or makes the inference within the time frame that is appropriate using the resources that we have available to us. What about the overall architecture of the human brain? What implications does it have? Well, I've mentioned many times during the course of the term the working memory bottleneck, the fact that working memory has a relatively puny capacity. And this Where's Waldo picture illustrates that point nicely. Somewhere in here, there's this guy, Waldo, who's very recognizable when you see him, but there's just way too much information in the visual scene for you to be able to just look and say, there he is. Conscious working memory has a very restricted capacity. And in fact, conscious working memory isn't a single system. As we saw in previous lectures, conscious working memory involves at least 3 different information storage places. There's the visual spatial sketchpad that stores visual and spatial information. There's the phonological store that stores phonological and order information. There's the episodic buffer that acts as a sort of sketchpad of working memory that facilitates transfer from one store to another. There's the central executive that oversees the operations of these and orders operations and so on. And of course, even within these stores, information decays very quickly unless it's rehearsed. In the case of our phonological store, it's rehearsed through articulatory rehearsal by either actually speaking it over and over again or rehearsing it in some way over and over again. In the case of the visual spatial sketchpad, it is the visual spatial scribes, that is, diverting attention back to that point in the visual scene, for example, to refresh your memory. Now, the working memory capacity that we have is also a gateway into long-term memory. So our visual semantic memory, our episodic long-term memories, our semantic long-term memories, they are all encoded in through their being present in working memory and then consolidated into long-term memory. And of course, working memory pulls up information from long-term memory during the course of problem solving as well. Important things for us to remember, particularly with regard to human inference abilities, is that working memory capacity and duration are limited. Information decays in working memory without rehearsal. The original estimate of the size of working memory was Miller's famous paper, The Magic Number Plus or Minus 7, where he estimated the range of the capacity of working memory, which he called short-term memory, as ranging between 5, 7 minus 2, and 9, 7 plus 2. Nowadays, contemporary researchers recognize that there is no single memory store, and so the capacity of individual memory stores is a more appropriate measure. The visual spatial sketchpad, for example, can store 3 to 4 items having 1 to 4 features. Again, the number of items depends on the complexity of the item being stored. You'll get 3 items if you've got 4 features in all likelihood. You'll get 4 items maybe if you can get 1 or 2 features. And similarly for the phonological store, right? 3 to 8 items is what it's estimated as, and those items are tied both to the size, that is how long it takes to speak them, how complicated they are, and their similarity to one another. Working memory size has a strong genetic component as well. So there's a limited best capacity to modify it through brain exercises and things like that. We can adopt some strategies like chunking to help facilitate keeping things in our working memory by organizing them into groups, increasing the complexity, thereby decreasing the number of individual items, but increasing the overall number of items. And working memory decreases in size with age. It's implicated in fluid intelligence, which we'll see corresponds to operations that are categorized as System 2, and it serves as a gateway to long-term memory. In the next module, we'll turn our attention to human and proto-human evolution and how the typical environment of human and proto-human evolution, together with the sorts of problems that that environment would present, help to shape our inference-making strategies.